Okay, so now we're going to talk about something called diagonalization. And what I've written out here is an array of every possible fast-growing function. So on the horizontal, we have the inputs to the functions getting higher, so 0, 1, 2, 3, 4, 5. And going down, we have the subscript of the fast-growing hierarchy going up, so 0, 1, 2, 3, 4, 5. And this extends to infinity in either direction. Now, along the diagonal right here is what we have is the fastest growing possible function, basically. And we're going to use infinite ordinals to our advantage to come up with a definition for this, basically. Let's just write down omega as our fundamental sequence again. So I'm going to include 0 in this, or whatever, just because we have 0 as an option here, something that we can plug in. Blah, 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 off into infinity. So now we define f sub omega, our infinite ordinal, of n, to equal fn of n. So basically what we're doing is we're taking the nth element of the fundamental sequence and we're plugging it in. So if we imagine we had f omega of 3, for instance, we'd take this element here and then we'd plug that in to omega to get f3 of 3. If we had f omega of 100, same thing, we take the 100th element and that would equal f100 of 100. So this is this might not be so clear why this makes any bigger numbers, because before we could have just plugged in 100 into here if we wanted and done the exact same thing. So the rationale behind this might not be clear right away, but when we get into omega plus 1 and stuff, this will become clear. But I just wanted to kind of flesh out the idea of what diagonalization is. And this, coupled with the recursion of the fast-growing hierarchy, can create very, very large numbers. So we're going to go on to more of that in the next little bit.